Hi, my name is Nasim. I'm a postdoctoral researcher at IDIR lab at the University of Texas at Arlington and one of the contributors of SOCKG. I'm going to present to you a technical overview of SOCKG, or Soil Organic Carbon Knowledge Graph. This work is a collaboration between the University of Texas at Arlington and the United States Department of Agriculture. SOCKG is a knowledge graph that integrates diverse data sources on agricultural practices that can help carbon sequestration in soil across time periods and geographical location. And it's not just a knowledge graph, but it's a set of tools for query and analytics, and it can also support a wide range of users, from farmers and researchers to policymakers, and can serve for different purposes like doing research, benchmarking, and policy making. To model the data, we had several iterations with USDA collaborators on our design choices, because we needed to have a deeper understanding of this agricultural data. And we had some special focuses on the following. First, we wanted to standardize our special features. More specifically, we integrated our data with Nowhere Graph to enable spatial query. We used predicates from Nowhere Graph. We also did some standardization for measurement and units through adaptation of QUDT. So basically, every measurement is modeled as a resource with a parameter that it's measuring and uses QUDT predicates to indicate the numerical value. We also integrated our data with some external vocabulary to ensure interoperability. So this is an example of our measurement and units. Here we can see a residue management sample, and we can see all other classes that this instance belong to. For example, the experimental unit that this sample was measured from, the treatment that it is associated with, and then we follow the standard approach we defined for numerical information. We retrieve the measurement that were taken from the sample. So this sample has some measurements, and here we are only measuring above ground biomass and grain dry matter. So we only kept measurements that measure these two things. And then from these measurement nodes, we retrieve the QUDT quantity value. I have actually clicked on this. You can see the decimal values of this measurement. And also, when possible, we linked substances to authoritative CAS, or Chemical Abstract Service Register numbers. We also integrated our ontology over 60% of our ontology with NALT, or National Agricultural Library Thesaurus. NALT actually standardizes the agricultural terms. So it helps us to standardize our ontology, and also it's good for interoperability. Here you can see a screenshot of our website, which features various tools and query endpoints. I invite you to visit the website and explore other resources that are made available. For instance, we can download the data. It is available in different formats: RDF Entryable, RDF Turtle. We have also made available our ontology file. We have also provided a GraphDB Sparkle endpoint, which allows users to perform Sparkle queries. We also offer several dashboards that allow users to filter and explore the data interactively. For example, in this dashboard, users can see how the experimental units are spread all over the US. Then users can filter experimental units by their state or their county, and then see the list of experimental units matching their filtration. They can also click on one of our experimental units and see more details about them. For example, some data table and visualization. They can also explore our treatments by filtering them by several criteria and see the matching data accordingly. We also provide a data cube for SOCKG, which follows a lattice data structure. Our data cube includes 12 dimension variables, including time, location, and treatment, and one measurement variable, which is stock or soil organic carbon. So we actually pre-computed tables that are a combination of all these dimensions, over 4,000 tables. Of course, this pre-computation helps better user experience. For example, here you can see a table where state is the grouping dimension, and another table where we have more dimensions for grouping, for example, grazing rate and the year. Although we provide SPARQL API to our data cube, we also provide this exploration interface, which makes it easier for users who are not familiar with SPARQL to explore our data cube. They can choose their dimension here. They can choose the aggregation function they wish to. It can be averaging, summing, and so on. And then we have several visualizations and tables that they can choose from for the display options. Another project that we are working on is OntoDoc, which is a project that generates documentation for knowledge graph resources automatically. So we were motivated to work on this project because the original SOCKG raw data files contain a large number of domain-specific terms, such as these terms that you can see here, that are opaque or cryptic for users to understand. So we actually worked on this tool that automatically, using a agentic LLM framework, generates description for our resources. These descriptions are inferred by neighboring nodes in the knowledge graph, data samples associated with the properties, and also some external resources such as Wikipedia. And of course, the outcome is going to be the descriptions of the resources. Let's take a look at one example here. We have, for example, a class, an object property, a data property, and another object property. These are from our knowledge graph SOCKG, and you can see the natural language generated description by OntoDoc here. We also use OntoDoc on other knowledge graphs in Proto-OKN. For example, here you see one object property from SOCKG or a class from Climate Models knowledge graph. Another thing that we are working on is generating natural language queries automatically, and then generating their corresponding SPARQL queries automatically. This is because we wanted to, of course, emphasize on the practical applications of SOCKG. And these are actually 3 examples of these automatically generated natural language queries. And using our text-to-SPARQL tool, we have generated the corresponding SPARQL query of this natural language query, which is the first query in my previous slide. And then we can execute this SPARQL query to see the results, which basically helps us eventually make this knowledge graph more accessible to the users. And finally, I would like to talk about this tool, Ontology Explorer. So like relational databases that this schema can give us some understanding about the data, ontologies also play similar roles in knowledge graphs. But the thing is that there are many knowledge graphs that don't have declared ontology. So we actually developed this tool which visualizes the ontology of knowledge graphs. If the knowledge graphs have already declared ontology, we just visualize the ontology. But if they don't, we infer the missing components from the data. So the input of this tool is a SPARQL endpoint, and the output is the ontology. Except for give us better understanding of the data, ontologies can help us for downstream tasks like NL, or let's say text to SPARQL, like the tool that I discussed in my previous slides. And also it can be integrated with OntoDoc for an end-to-end user interface, because OntoDoc requires the ontology in order to create descriptions for the resources. Our tool, you can actually see a screenshot of our tool here. On the top right, we can choose which endpoint, which SPARQL endpoint we want to use, and then we visualize the ontology. We can have some control over visualization as well. And we also show the list of classes and object properties here. This is the visualization of our classes and object properties from SOCKG, visualized by Onto Explorer. And I have zoomed in a little bit here to show that we can show some hierarchy using these, let's say, boxes. Actually here, this box shows a measurable entity, and under that we can see all the other classes that can be measured, and this class is connected to this class measurement by has measurement property, which is actually very similar to an example that I gave you earlier about measurement and unit standardization. So here we can see it on our ontology, how we modeled it. As I explained, we can choose our SPARQL endpoint and visualize any of the knowledge graphs. Here you can see a visualization of a saw graph view. And with that, I conclude my presentation, and I would like to thank all the team members who have contributed to this project, from USDA collaborators to faculty and student researchers. Thank you.